Hello everyone, my name is Dinal and with me today is Zihua. The project that we are going to talk about is called Real-Time Thermal Comfort Prediction. So first of all, I'll just go through an introduction about the project and what we aim to do with it. So thermal comfort is essentially a condition of mind for people that is essentially an index about how comfortable we are thermally in any indoor environment. As you can see in this image, there are multiple different things that essentially affect it, or rather equipment that we use to make sure that we are in a comfortable environment. The fan, the AC, the ventilation system is all part of that. In most buildings, there are automated systems that take care of our thermal comfort. And what these systems do is they use real-time sensing with different sensors, and they use actuators, which essentially are the fans and the heating system, to control the temperature such that the people inside the building are comfortable. So what we thought is, in our project we wanted to go a step further. As you can see in this image, what we try to do is introduce this component of prediction into real-time sensing. And the idea is to essentially create a predictive model that can be stacked on sensing networks such that the algorithms that work to control the temperature can have better performance by utilizing not just the information right now, but also predicting how temperature could vary in the future. For this case, in our project, we are mostly focusing on real-time sensing and prediction. To that end, we wanted to find out a predictive system that essentially has these three properties. The first property is the model itself should have high accuracy. The second is it should have low overhead. The reason is whatever model that we introduce should stack on top of an existing system. So it should not overburden an existing system. And finally, it should be very robust to sudden changes. The system that we design is uh, as I've shown in this image. It essentially has two components. The first component is the sensing part, which we use a Zigbee sensor network, and we collect real time. We collect temperature data from different indoor settings, and afterwards we use those temperature information to train different kinds of machine learning and deep learning models, and to identify what sort of model fits our situation the best. In our case, we identified that linear regression, which is a online machine learning algorithm, has the best fit for our scenario. First of all, Zihua will talk about our data collection methodology and demonstrate how our sensor network work. Afterwards, I'll talk about the machine learning algorithm and how it works.
So we use three Talos B modes based on TidyOS in this project. One is used as base station, this one is base station, and another two is used for sensing the environmental temperature and humidity. At the beginning, we use two modes to detect the temperature and humidity, and directly send them to the base station via radio, which works fine for indoor one-room data collection. But due to the limitation of the transmission distance, we can't let this simple network work in multiple rooms or collecting outdoor temperature. So we developed a tiny multi-hop wireless sensing network. One node sends data package to the relay node. So this one sends the data packages to the relay node, and then the relay node will take the packages and resend them to the base station. So based on this wireless sensing network, the maximum transmission distance doubles and the whole system can be more efficient. Then I will demo this to you in this video. So as you can see in the terminal, we have two most readings. The first number is the node ID, and the second one is the sequence number. The third one is the temperature, and the fourth one is the light intensity. And the last one is the humidity level.
Now that Zihua talked about and demonstrated our sensing platform, I'll talk about our machine learning algorithm and why we picked it. We essentially we initially tested out with different kinds of models, and we finally realized that the machine learning model called linear regression seemed to have the best fit for our scenario. And these are some of the reasons why this model worked. Now, machine learning algorithms or this linear regression is an online model, so it is quite robust. Additionally, we realize that it can have predictions with an accuracy of around zero point 0.2 milliseconds, and that's very fast considering our case. Though machine learning algorithms might not be able to capture excessive complexity like its more uh, better counterpart deep learning, for our scenario, we saw that linear regression worked well. And in this slide, you can see a bit of the code for our linear regression model. Now that I've talked about our actual model that we used for predictions, I'm going to demonstrate how it works. So initially, uh, I've opened a terminal where the code resides, and then I've activated TensorFlow. I can show it again. So first I activate the TensorFlow library, and then since I've coded everything with Python and use TensorFlow, we can just call Python, and we call the demo 4. We have created a separate set of datasets for called demo 1 to demo 5, and so in this case I'm running the fourth demonstration for an actual dataset that we created. As you can see, in this interface we show 20 time steps of predictions, and the black shows the actual temperature while the red is the predicted value. And on top of it, at this point we show the speed at which each prediction is spitted out from a model, and we can see, as I mentioned earlier, that for one prediction it takes around 0 0.2 milliseconds. Now, even though the prediction was a bit off, as you can see in this video, it quickly converges to its actual value, and after some time it keeps on predicting the temperature variation quite accurately. Since this dataset is very large and it will take a long time to show all the possible variations, I'm just going to show what will happen at the end. So this image shows the entire dataset that we used to test our model, and as you can see, for small locations, even though there are some certain errors in prediction, it quickly converges to its actual value. And in fact, this is a dataset that we collected from our own system. Next, I will show how our model fares with a dataset that we found online. This dataset is something that we did not collect, and it is not an indoor setting. Instead, it is an outdoor setting, more or less the worst case scenario for a model. Even then, I'm going to show that the overall prediction accuracy is quite okay. As you can see here, the temperature varies quite rapidly, and there are very sudden fluctuations in the temperature. So our predictions might be slightly off, but it still captures the overall variation or the trend of how temperature varies. Again, I will show how the total prediction looks once the entire dataset has been predicted. As you can see, even though there is a bit of an error with the predictions, it sort of captures the trend quite well. I will zoom in and show it again. So as you can see, Even though this model was not initially developed for outdoor datasets, still our entire system, sensors included, can be utilized to create a predictive model that can be employed in actual heating and ventilation systems.